welcome to Wing Design Tutorial 4, Use SolidWorks Simulation for Structural Analysis. And in this tutorial we are going to create a static simulation of our wing using SolidWorks. And we're going to simplify this geometry by selectively including parts. We're going to constrain it using fixtures. Then we're going to apply a force at the wingtip and evaluate stress and deflection. Then we're going to use some advanced visualization tools to highlight areas where the stress is maximized. And then lastly, we're going to apply some torque and see how the wing behaves in torsion. Okay, so here we are in SolidWorks, pretty much where we ended up at the end of tutorial 3. And we're now going to take this assembly file and do some stress analysis on it. So to do that in SolidWorks, we do it using simulation. So you've got various tabs along the top here, and if you click the simulation tab, there's a little icon at the top here that says new study, and if you click that, it will create a new study, and let's just call this my study number 1. Doesn't really matter what you call it. And it starts off as a static simulation. Static simulation is the default, and that's the one we want. And actually we can leave it exactly as it is there. It's the basic analysis is what we want to do. So if we tick that, and now this other little tab appears at the bottom here, however you labeled it. So my study number 1 is there. And we can still see our old model there, but now we've got a new window here, which is the static study that we're going to be doing. Okay, so first thing we're going to do is simplify the model a little bit. So we're going to focus on analysis of the spar, because this is the bit that's carrying most of the load. And in fact, from the Excel spreadsheet work you've done, the spar is the thing that's carrying the load. The rest of the structure is there really just to create the aerodynamic surfaces. So we're focusing our effort on optimizing the spar, so that's what we're going to model. And we always try and model the simplest thing as we can to start off with. Okay, so let's get this thing simplified. So the things we do need are the spar, so we definitely need that, and we need the vice thing to hold it. So these other things that we can get rid of, and if you do shift click on these, it'll do them all, and then right click and you can do exclude from study. So they've disappeared. We need to get rid of the leading edge and the 2 trailing edge bits, and exclude from analysis. Okay, and there we go, and we're left with just the important bits to start off with of the kind of vice, the thing that's holding it, and the spar itself. Something else we're going to do to make our lives easy, we're interested in simulating the behavior of the spar. The vice, we're not really interested in deflection of the vice. The vice is going to be much stiffer and stronger than this, so we're going to assume the vice is a fixed material. So if we go to the vice, and if we select both of those, and select both of those, right click, and then make rigid, all that does is it keeps the shape in the simulation, but it just means it doesn't move. And that's just good practice, because it's not going to move a tiny amount compared to the foam board. But we're then going to fix it. Okay, so there are parts. Connections, by default, if these things are touching, they're connected. So if you've made your vice the same distance apart as the beam, then they will be connected. If they're not touching, they won't be connected. So it just, there's a certain tolerance, but basically if they're on top of each other, they will be connected. Okay, fixtures next up. So these are things in the simulation we want to hold fixed. So in our sort of real world, the vice is fixed. So what we're going to do is apply some fixture treatments to this vice. So what we're going to do, right click on fixtures, and then click fix geometry. And nice little graphic here, but it's just showing us if we click a surface, that's the bit that's not going to move. So for the vice, what we're going to do is top and bottom surfaces, assuming those bits can't move. Little green icons appear on there showing that these things are fixed. And so yeah, when we apply load to our beam, these things aren't going to move. Next up on here on the list is external loads. So let's add a force to our beam. and you can see here it's trying to apply a force whenever I point to a surface. It's doing kind of force normal to it. We're going to be applying a load at the end of the beam, so I am going to select that. That's pushing in, so we need force going up. So what I want is a selected direction, and I'm going to pick a vertical side like that, and you have to click on force to make it wake up for some reason. Anyway, so that's down. We're going to have any hanging weights off it. I'll tell you what, I'm just going to reverse that just so it's going up, so we can pretend our wing's kind of lifting and the force is going up. See, if you're testing in the lab, gravity's acting down so that your force goes down. And we've got 1 Newton on there, but if we go to our spreadsheet and if we look at the calculate bending moment, actually the point load at the wingtip for the design inputs I've got here, so you need to check they're going to be the same for yours, is, let's round that up to 20 newtons. So tell you what, let's just put 20 newtons in there. So 20 newtons. Okay, so it's over that surface, that's right. In the lab, whatever, you may be hanging a weight off there, but it effectively does the same thing. So far so good. In Excel, basically you just did one section and applied forces to it, but the magic of finite element analysis, as it's called, is the code will divide this up into lots of elements and solve all of them, whereas you solved one. We can split this up into many pieces, and the software will solve them all simultaneously to get us our deflection. So to do that, we need to generate a mesh on this, divide it up into smaller blocks. So if you right click on mesh and then do create mesh, and to start off with, just really get a low density, so I'll wind it right back. We'll make it as simple as possible to start off with. Tick that, it'll trundle away, and there we go, it's created some sort of mesh. And so each of those sort of tetrahedron elements of that mesh is now a separate kind of solid that it solves the equations of solid mechanics for, and they all become simultaneous equations in a big matrix, and then you solve it by inverting the matrix to solve all of those at the same time. So it's the sort of thing that computers are really good at. Each of these things is no more complicated than your Excel spreadsheet, but the software will solve hundreds of them in parallel. Okay, I think that's looking good. I think we're ready to run it. Yeah, let's run it. So to run the study, click this little button here, run study. And we've got something, excessive displacements for calculating this model, blah, blah, blah. This is a wing, so it does bend quite a lot. So let's just read what the options are. So yes to solve with a large displacement flag activated, no to solve with small displacements. I'm going to be a bit cheeky and say no because it's quicker. It is more accurate if you put large displacements on, but no is a bit quicker. So I'm going to do that to start off with. There we go. And we've got a solution. So let's have a look at what it's doing. Beam's obviously gone up at that end, and this plot here, stress, von Mises stress, so this is kind of the, it doesn't have a direction, but it's the kind of average stress in the material. So you can look up what the definition of it is, but in terms of tension and compression, it's this kind of magnitude of stress. And what this is saying is our peak magnitude of stress is at the top and the bottom at the root. And if you know anything about structures, that's exactly what you'd expect. We applied a load at this end, and actually the load at this end is, the stress at this end is almost nothing. All the stress is at the end where you've clamped it, because that's where the bending moment is largest. The other thing of significance is that the peak stress is at the top and the bottom of the beam, and this comes down to the way stress is distributed. So if we're pushing up this way, the top bit's in compression, the bottom bit's in tension, and the middle of the beam's under no stress whatsoever. So it's what's called the neutral axis of the beam in the middle. The stress is 0, and the stress peaks at either side. So if your beam's going to fail, in this sense, it's going to fail by crushing up here and sort of splitting underneath there. What else can we learn? Because this is all blue, is not really doing anything. So the engineer in you thinks, well, if that's doing all the heavy lifting, that's where the beam needs to be strong, but the rest of the beam doesn't need to be strong at all. So the initial reaction would be, okay, well, why don't we just carve out that bit of the beam and get rid of it because it's not really doing anything, and we could save half the weight of the beam. And if you recall back to the giant foam board aircraft stuff, looking at conceptual design, the whole principle of the design of that aircraft to minimise the spar mass is that it's kind of a triangle cut out the middle of the spar. So you just have material where you need it. Inside the vise itself, it's all blue because all the load is being taken by the steel, which is like 200 or 300 times stiffer and stronger than the foam board. However, in practice, you are actually gripping it, so the thing is going to be stressed slightly because you're squeezing it. And what goes on in here can be a little bit complicated, but overall, you would expect this thing to fail just outside the vise. We can do some cool things with some plot tools, so let's actually have a look inside the beam, see what's going on. So if we go to plot tools and then do ISO clipping, it's a really nice feature here where you can decide the level at which you want to show the stress. So as we increase this, it's basically, you can see this arrow going up here in terms of stresses, so this is now only just showing the really stressed bit of the beam. And it's, as we expect, it's the top and bottom of the beam that's most stressed. And if we reduce that contour, we can gradually see more and more of the beam, the stress levels getting lower and lower. So in some ways, this kind of closed peg sort of shape, you could call this sort of structural optimization, but this is the shape, this is where the material is being loaded, so this is where you need to place the material in the beam. It's never quite as simple as that because you've got to hold the thing together, but this just gives you a visual indication of that. Okay, that's good. Let's actually turn off the clipping. Let's actually have a look at the displacement. So one thing you need to check, if you right click on that and go to edit definition, if you look at the scaling, the automatic scaled shape is actually increased by a factor of 1.6, so it isn't actually true scale. So generally things deflect tiny amounts, so you want to make it massively more exaggerated to see it. In this case it's pretty close, but actually for our purposes it's interesting to see what the true scale is. So let's just check that button, and yeah, it didn't make a huge amount of difference actually in our case, but that's how much that will deflect under load. And if we want to see how much that is, if we go to the displacement plot, you can see here it is deflecting, so this is now coloured by displacement, not stress, so it's not nearly as interesting as a stress plot, but the top bit here is displacing 5 times 10, so that's 50 millimeters. And if we go to our chart here, if we have a look on this, on our beam, looking at the deflection, it's not far off actually. So 0.7 along there, 50. So our XL prediction for the displacement of the beam was around 50 millimeters, and that's what we've got. So there's obviously quite a lot of moving parts between the Excel spreadsheet and this, but it's kind of showing everything is kind of working. There's obviously uncertainties in the kind of material properties, but if you use the same material properties in SolidWorks as you do in Excel, you should get about the right answer, which is encouraging. And while we're here, let's just check the stress level as well. So the peak stress in here was 1.4 times 10 to the 6, and if we go to the Excel, peak stress we got here was 1.2 times 10 to the 6. So that's not bad. We're getting reasonable correlation between what you'd expect from Excel in this simple calculation and what you'd expect and what you're getting from this more sophisticated analysis. Let's now look at how we can try and get a, let's say, more accurate answer, or more an answer, a higher fidelity answer, by increasing the mesh. So if we go back to our mesh again, and let's make a mesh that's a bit more fine. Okay, so we've got a lot more elements in it, and we could go even further if we wanted to work it up to near maximum. So this all takes time. It takes time to mesh it, takes time to solve it. You can see here now we've got a much finer resolution on our elements. and that means we can better resolve forces, particularly around the stress concentration. So let's try running that and just give you an idea of how long it's going to take. Okay, excessive displacements again. Yeah. We'll do exactly the same again. We're going to do no to use small displacements. Actually, that was pretty quick, wasn't it? If you do the large displacement one, it will take quite a lot longer when you do finer mesh. And what we can see there, if we look at zoom in, there's actually a lot more detail going around there, and actually the stress has changed. It's actually gone up. So as we've improved the resolution, the stress has gone up. Okay, now let's have a go at looking at applying a torque. And to do that, we're actually going to need an axis about which we apply the torque. So we're going to go back to our model. And if you remember, we made a little point in the middle of our spar. We're going to use that now. So let's just take any one of these sketches and show it. And then what we're going to do is insert reference geometry axis, and we're going to do a point and a plane. So we're going to pick a point, and then we're going to pick the face of there. You might be able to see it, but there's a little yellow dotted line come out, and that is now an axis which we can use to apply torques about. Massive, yeah, okay, don't worry about that. All the sketches have become visible. Let's just hide those again. Okay, that's fine. So now if we look down here, we've got an axis. So we can now use that to apply our torque. So going back to the study, we've got external loads, apply a torque, and it's asking for a face. So let's do it about that face, and it's asking for a, well, we need an axis which we'll do about it. So we need to find that axis. Axis 2 is the one I've just created. Tick that, and let's put in 10 Newton meters. If you've done it right, you should see these kind of magenta arrows sort of flowing round in a circle around the end of the beam that shows that you're applying a torque around there. If you've done it wrong, these arrows might be pointing in random directions, whatever. That's what it should look like. Press that. So turn off the force. We suppress the force. Okay, and our mesh, wind the back a little bit. Just makes it run faster. That's more than enough points to make it run. Okay, everything else is the same, so let's run that. Okay, and we've now got a twisted beam. So hink spacebar, and in the end that does a view straight on. Okay, so we can see there that we've applied a torque, these magenta arrows, and it's made our beam twist. And if you remember, if we just check on here, edit definition, it's true scale, so this is actually how much it would twist if we applied 10 Newton meters. Going back to what the requirements were, that the torsional compliance should be no more than 3 degrees per Newton meter. So if we're applying 10 Newton meters, then it should be no more than around 30 degrees. You can find the height of this and do all sorts of geometry with sensors and everything else. It's actually easier probably just putting a ruler on the screen, but if you measure the angle of here, how much it's twisted, that is probably around, I don't know, 20 degrees. So at the moment this spar would meet the torsional compliance requirement in terms of the number of degrees twist per Newton meter is less than the set value. Okay, that's good. So we can do bending, we can do torsion, we can do both at the same time. So let's just unsuppress that. Let's just run it. No again. And there we go, we've now got a beam that's twisting and bending, so you can look at the combination of the two. In terms of the requirements for your design, they only really need to be looked at in isolation. They do add up together, but it's sufficient to consider them in isolation. Okay, so that's pretty much what you need to know about doing this stress analysis. It's a great tool in SolidWorks. You visualize what's going on, but all the time you're kind of referring back to Excel, because Excel is the fastest way of doing this. It takes a lot longer to make something in SolidWorks. It's relatively quick, but if you can design something in Excel and get it right, it's instantaneous when you change things. This takes a little bit longer, so you would tend to use this when you're close to your optimized geometry. And lastly, what we'll do is, just to throw everything at it, we'll just have a look at what it does when we put all the other components in. And this is really more out of interest than anything else, because this is the made load carrying bit. So let's go back to our parts and let's select all of these and include analysis. Same with these, include analysis. And let's go back to our mesh. So all the bits appeared once I tried to make a mesh. Let's do a medium mesh. There we go, so it's meshed the whole thing. While we're doing this, these control surfaces are not constrained because they're on hinges, so it actually makes no sense applying loads to these. So what I'm going to do actually is remove these, because it doesn't make any sense to include these. Okay, so we're applying a force and a torque. Those are things all the same, so it's remembered that. You can still see those on there. Okay, let's give it a try. So no. And there we go. We've got a wing that is bending and twisting under load. So if we're doing the section clipping, we can see that in terms of brightness of colour, it's the spar that's got the most load on it. So the rest of this structure is pretty much blue. It's got some lighter green on it, but it confirms that it's the spar that's doing the heavy lifting. The rest of this really is just secondary structure. Well, because we're applying load on this spar, so some gets distributed here, but it's mainly in the spar. And if we look at our clipping, we can see that indeed it is the spar that's carrying the load. Okay, and the very last thing we can do, and this is kind of eye candy for engineers, we can make an animation of that. So quickly just show you that. So if we can do an animation. And there we go, we can see our wing bending and twisting under load. Bear in mind, this is actually not really animating very much, apart from just changing it from the zero load condition to the full load. It's a linear analysis essentially, so we're not really seeing much from the animation, but it's quite good for the human eye to see what's happening as you're applying a load to a wing. You can see the change in colour and change in displacement. Okay, so there we are. We've done our stress analysis of the wing. So what you've seen is how you create a new study. You need to choose which parts you want to include in it. So you generally do a simplified model to start off with, so you enable or disable those. So we took the vise and we made it rigid, so in the meant that we were applying forces to it, but it wouldn't displace. We just assumed it was going to be infinitely rigid because it was made of steel. Then we applied some fixtures, so we made the vise fixed on either side, so now it's fixed relative to the world. Then we looked at some external loads, so putting a force on and putting a torque on. Then we looked at making a mesh, so dividing it up into lots of cells, and then running it and looking at the stress and displacement of the spar. So you're now equipped to do the full design process for a wing spar and associated secondary structure. You can design using conceptual design using simple theory in Excel. You can draw your wing up using CAD in making parts. You can make an assembly, and then from this assembly we can do some structural analysis and compare that back to what we predicted from Excel. And then from this, hopefully you can work towards making a wing spar that meets all the requirements, but it's the minimum mass of material used to do so.